Hey Algebra 2, this is a little recap of the first 2 days of Unit 8 so that you can get started in your work today and have all those ideas that we've seen so far summed up. So a polynomial equation is an equation that can be written in the form some number times x to the power of some exponent. Now I'm using those subscripts, that little 1 underneath the a and underneath the e. It's not the same as the base in a log expression, it's just kind of like a description. Because what I'm going to do then is I'm going to say a polynomial can be a1 times x to the power of e1 plus a2 times x to the power of e2 plus a3 times x to the power of e3. And I'm just going to do a dot 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 after that. So I think you get the pattern there. And the reason I'm not just using different letters for the coefficients and the exponents is because then I can just be lazy and say this definition describes a polynomial as long as a is any whole number. So there I've just described, oh I'm sorry, that's not true. As long as a is any number, doesn't have to be a whole number, could be anything, could be irrational, rational, pi, whatever, and e is any non-negative integer. An integer is really what you all think of as a whole number. It's like the numbers 1, 2, 3, 4, 5, 6, etc., and 0, and -1, -2, -3, etc. And whole number in math really is just a limited set of those. So I'm going to say integer, but I'll put whole number in parentheses here, because that's really, like, I think in a lot of your minds the same thing, which is totally fine at this level. So what I was doing when I was using those subscripts, that a sub 1 and e sub 1, I was being lazy. So I was just saying that a is any number and e is any non-negative integer, which means that I don't have to do the description multiple times. I just said that about e, and it applies to every single one of the exponents in my expression there. Okay, and then I wanted this to be an equation, so I just have it set equal to y at the very beginning. Now, that definition of a polynomial equation is a little bit hard to understand because some of that notation is new, and then we've got that dot 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 at the end. So this other way we've described it is an expression that can be written in the form, I'm going to say sum of terms, so sum means addition, sum of terms that look like, and here we're going to see some of the same language, any number times x to the power of a non-negative integer. And so there are some things that fall into this form that you might not expect. So examples of polynomials, just the number 7 is a polynomial because it can be written as 7 times x to the power of 0. So that coefficient is any number, we've got times x, and the exponent is not negative. That's why I didn't say a positive integer, because I want to count 0 as well. So I could have negative 2/3 times x to the power of 4. That's a polynomial. Something that's not a polynomial, so a non-example, would be 5 times the square root of x, because this is really 5 times x to the power of 1/2. Another non-example would be 1 divided by x squared, because this is really x to the power of -2. So if you're seeing x under a square, cube root, etc., that's no good. If you're seeing x in the denominator, that's no good. One last one that I see sometimes is x in the exponent itself. So that's actually exponential rather than a polynomial. Okay, so that's the first bit of vocab. We know that some polynomial equations can be rewritten in factored form, and so the last couple of days we've been looking at those specifically. So let me give you an example of that. I could look at the polynomial y equals x cubed plus x squared minus 6x. And that certainly fits my form of what a polynomial equation is, but I could also rewrite this. So I could first look at it and say, okay, well, x multiplies into all of those terms, so I'm going to factor out an x. And then what's left in my parentheses is quadratic, and we know how to factor quadratics. So I'm going to go ahead and rewrite this. So it turns out the beginning, that first polynomial equation that I gave you as an example, can be rewritten in a factored form. Okay, and so each of those factors now give us a little bit more information. Before I go into what information exactly those factors give us, I want to introduce one more vocab word. So the degree of a polynomial equation is the value of the largest exponent that one of those x's is being raised to. So we were just looking at y equals x cubed plus x squared minus 6x. And so the largest exponent there is the 3. So for this one, the degree of this polynomial is 3. That degree is going to correspond to the family of functions that the polynomial equation fits into. And so we're going to have a little bit more of that in a minute. I lied, we're going to have that right now. So a first degree polynomial equation is going to be something in the form y equals some coefficient times x to the power of 1 plus some coefficient times x to the power of 0, which I'm just going to leave as a whole number. Okay, so let me give you an example of this. An example might be y equals 1/3 x plus 4. Okay, the first degree polynomial is known more commonly as a linear function. Linear function might look like this. That's a straight line, just believe me. Or it might look like this. Alright, and so when we're looking at these families of functions, I want to also keep track of something called their end behavior. So end behavior means as x values increase, going towards infinity, or as they decrease, going towards negative infinity. Maybe I'll use a different color for that sign. We're keeping track of what's happening to the outputs. So here, as x values get really big, y values get really positive, and as x values get really small, x values get really negative. So the end behavior for a first degree polynomial is that it's starting negative when x is very negative, and it's ending positive when x is very positive. So on the other side, this other example of a first degree polynomial that I drew, as x increases, y gets very negative, and as x decreases, y gets very positive. Now the only difference between these two graphs is that one of them has a positive vertical stretch factor. So this is where our vertical stretch, which we use as a, is greater than 0, and this is one where a is less than 0. Okay? And I think for now what I'll do is I'll just write this as a times x to the first plus b. I'll just use a different letter there. Alright, so let's go to the next one. A second degree polynomial equation, better known as a quadratic equation or quadratic function, would look a little something like this. Just like a polynomial. Could also look like this. Alright, as x gets very positive, our y values get very positive, and as x gets very negative, our y values get very positive. So for this one, the end behavior is the same on either the left or the right side of the x-axis. This is when a values are greater than 0, and we're looking at a general form of y equals a x squared plus bx plus c. Okay, on our other one, as x gets very positive, y gets negative, and as x gets very negative, y gets negative. So again, we're seeing that the left and right end behavior is the same, and in this case, when we've got a parabola opening downward, that's when we have a being less than 0. Alright, third degree polynomial is going to be in the general form y equals a x cubed plus b x squared plus c x plus d. Okay, so a, b, c, and d can be any numbers. We've got two different pictures here. So we might see a cubic looking like this, or we might see a cubic looking like this. And I'm going to redraw this part of it a little bit. I really want this to keep going out like that. Okay, so as x gets very positive, y gets very positive. As x gets very negative, y gets very negative. So here again we're seeing that negative end behavior on the left, positive end behavior on the right. That is when A values are greater than 0, and when A values are less than 0, on the right, as x gets positive, y gets negative, and as x gets negative, y gets positive. So just to recap what we've got so far, first degree has end behavior that's different on the left and right, second degree is the same, third degree is different, fourth degree, again, is going to be the same, okay? So it could either open up or open down, but we're going to see this left and right end behavior being the same for this fourth degree polynomial. Okay, I'm going to go through two more. A fifth degree is going to look like this, or like this. Oops, that's not right. Like this. You can see I'm just doing these quickly. Positive end behavior is positive, negative end behavior is negative. So we're seeing for fifth degree that the end behavior is different again. This is for A is greater than 0. If I look at A is less than 0, so a negative vertical stretch factor. As x increases, y decreases, and as x decreases, y increases. Okay? And the very last one, we're looking at a sixth degree is going to look something like this. So we'll see end behavior that is the same on the left and the right again when A is positive or when A is negative. So what we did was we realized that that there were some patterns here. Okay, so let's go back one more time. First degree, different end behavior. Second degree, the same. Third degree, different. Fourth degree, the same. Fifth degree, different. Sixth degree, the same. And so what we realized was that for an even degree, we were going to have end behavior that was the same. So it was either going to be plus plus, or it was going to be minus minus. And for an odd degree polynomial, we saw that the end behavior was going to be different. So for positive A values, it was going to be minus plus, and for negative A values, it's going to be plus minus. So I'll go through here. This is when A is greater than 0, A is less than 0, A is greater than 0, A is less than 0. So this was one of the summaries that we did at the end of one of the classes. And this is really important because it allows us to really quickly look at an equation and know what's happening on either end of the equation. So I said earlier that if we had a polynomial equation in factored form, that this was going to give us some really helpful information. So one of the most helpful things it allows us to do is find the x-intercepts. And in the context of polynomials, we've got another name for x-intercepts, which is roots. So you're going to hear me using that a little bit. And we know that x-intercepts occur when y equals 0. So in order to find these roots, we're going to be plugging in 0 for y and then solving. And so right away we can see that if the polynomial is in factored form, then I'm able to make use of the zero product property without really having to do much work. So I know that there are going to be solutions to this, aka x-intercepts or roots, when x equals 0, x equals 2, and x equals negative 3. So from a sketching perspective, this is really sweet because I can just go into my picture, into my sketch, and I can put an x-intercept at 0, 2, and negative 3. I'm going to make a little space for myself here. And then we just talked about the end behavior, so I know that this is a third degree polynomial because if I multiplied this x to the first by this single linear factor to the first power times this linear factor to the first power, I'm going to get an x to the third term when I multiply it all together. So I know that this is a cubic that's an odd degree, and so my end behavior is going to be negative on the left and positive on the right. So I really just have to check in two places. for whether my function is going to be above the x-axis or below the x-axis. And so I'll go in and I'll say, okay, well, let me check something in between -3 and 0. So I'll plug in -1. When I plug in -1, I'm going to get a negative number for that first factor, a negative number for that second factor, and a positive number for that third factor. I don't even care what the values are. I just know that a negative times a negative is a positive, and a positive times a positive is a positive. So I know that in this region, my outputs will be positive. And then I'm going to do that same thing one more time. I'm going to look for something in between 0 and +2. So I'll plug in +1. So when x equals 1, I'm going to have a positive times a negative times a positive, and that's going to be negative overall. So then I can go in and I can make this picture that has outputs that are either above or below the axis or on the x-axis in the appropriate places. So my graph is by no means perfect. It's just a sketch. It's likely got the wrong stretch factor, so it probably doesn't go as high or as low as it should, but that's okay for right now. And in fact, on the second day of Unit 8, we started to refine this a little bit. We started to figure out what would happen if some of these linear factors weren't linear factors. Like, what if this were an x squared? Or what if this were an x minus 2 to the power of 3? So we're going to look at some examples in Desmos, in the Desmos activity, and then you're going to continue thinking about what happens with equations in factored form, with polynomial equations in factored form.